Hello everyone. Here are our notes on 8.5, equations in a Cartesian coordinate system. So our objective today is to graph equations of lines, to find the slope of a line and the slope through 2 points, and to find the solution to a system of equations. So a Cartesian coordinate system, an xy axis, has a horizontal x-axis and a vertical y-axis. So here's our x-axis, here's our y-axis. When we graph vertical and horizontal lines, remember that an equation is just a rule for what points are included in our graph. If the equation is y equals 7, then our rule says that all the y values are 7. So in this first example, y equals 9, the rule is all the y values are 9. I'm going to get out a ruler here so I'm neat. So I am going to graph a horizontal line where all the y values are 9. So I might have this point 1, 9, 4, 9, 9, 9, negative 5, 9. All the y values are 9. When you're graphing a line where the equation says x equals something, like x equals negative 3, then the rule says all the points have an x value of negative 3. So our example here, these are kind of small, there we go, says all our x values are negative 5. So I'm going to draw a vertical line, if I can get my ruler straight. Where all the x values are negative 5. So y equals negative 2. That's going to be a horizontal line where all the values, y values, are negative 2. Sorry, I can't get this totally straight. And the line x equals 0, that's just our y-axis, right here, where all the x coordinates are 0. So that's how we graph a vertical and horizontal line. Now, I want you to take a break and go to Desmos.com and complete the activity below. Type in y equals mx, and when asked, put the m on a slider. And then go through and answer each of the questions here. And just familiarize yourself with equations in the form y equals mx plus b. And then come back to this video. All right, so let's talk about lines. When we put an equation in Desmos, y equals mx plus b. So hopefully you went to Desmos and you did this activity. When you move the when you move the m back and forth, you're changing the slope of a line. And when you change b, you're changing the y-intercept. Let's go to Desmos here. So let me turn around so I can have my keyboard for a second. So I'm putting everything on a slider. And when I move m is my slope. So this is a positive large slope. My line looks like it's a very steep slope. when the slope gets closer and closer to 0, it gets flatter and flatter. Here's a slope of 0, and then my negative slopes. A negative slope that's close to 0, and as the slope gets further and further to 0, it gets steeper and steeper. Now what does the B do? The B moves my line up or down, the same number of units that B is. And so that's an equation of a line. And we're going to look at the algebra behind the equation of a line. So first of all, we're going to look at slope. Slope is just the number that describes the steepness of the line, and if it's going up or down as you move from left to right. We calculate slope as change in my y values divided by change in my x values. Most of you remember it in algebra class as y2 minus y1 equals x2 minus x1, and it doesn't matter which points you choose to be point 1 and 2. So let's look right here. This is the point 1, 3. Right here we have the point 2, 6. And if I want to calculate the slope, I can take, let's make this point 1, this other one point 2, change in y values, 6 minus 3, over change in x values, 2 minus 1, I get 3 over 1, or 3. Some of you will count out slope. 1, 2, 3, change in y, 1, change in my x. Notice if you go the other way, it's the same thing. So I can do 3 minus 6 over 1 minus 2. It just gives me negative 3 over negative 1, which is still a slope of 3. And one of the characteristics of a line is no matter what points you pick, you will always get a slope that's the same. So if I pick the point 0, 0, and I pick this point here, which is negative 1, negative 3, what's my slope? 0 minus a negative 3, 0 minus a negative 1, which is 3 over 1, which is 3. And that's characteristic of a line, and it doesn't have to be the whole numbers. If you pick these two decimals and you get the exact decimal and you calculate the slope between those 2 points, it will simplify to be 3. And that's one of the characteristics of a line, is the slope is the same no matter what 2 points you pick. So turn off the video or pause the video, and then I want you to find the slope of the line that goes through these pairs of points before, and then turn the video back on and we will go through it. Okay, what's the slope of the line that goes through the 2 points? 9 minus 4, and you can kind of just give a rough graph. 9 minus 4 is going to be here. Negative 5, 2 is going to be here. So we're guessing we're going to have a negative slope. So let's calculate it. Negative 4 minus 2, 9 minus a negative 5, negative 6 over 14, or negative 3/7. How about the slope that goes from 0, 3 to negative 4, 3? Can you guess that slope before we calculate it? It's a horizontal line. So it should have a slope of 0, 3 minus 3 over 0 minus a negative 4, 0 over 4, which is 0. And what happens if we want to calculate a slope between 10, negative 8, so somewhere down here, and 9, negative 8? Again, we have a horizontal line, negative 8 minus a negative 8, 10 minus 9, I have 0 over 1, which is 0. Now, let's add one more. I didn't have one of these, so I'm going to add them. What if the y-coordinates are the same? Or the x-coordinates are the same? So what if I want the slope between, let's just say, a line that goes through point 7, 6 and 7, -2? What happens then? What kind of slope do we have? Well, change in y over change in x. Notice I'll have a number in my numerator, but my denominator is 0. So we call that slope undefined. It is not 0. It is not 0. Some students, I even have them in calculus, they see that 0 in the fraction, immediately they say slope is 0. No, slope is 0 when it's in the numerator. When it's in the denominator, the slope is undefined. All right, let's move into a systems of equations review. So when we talk about a systems of equations, we talk about a set of equations where we have 2 or more equations. While a solution to an equation is the value for the variable that makes the whole equation true, the solution to a system of equations is the value of the variables that make both or all the equations in the system true. And we're going to talk about systems of equations with just 2 equations, but you can have systems with many, many equations. Now, there's different ways to find the solutions to a system of equations. First of all, by graphing. So what does it look like when we solve a system of equations? When graphing an equation, all points on the graph make the equation true. When graphing a system, you're putting 2 or more graphs on the same coordinate axes. And the point that falls on all graphs are the solutions that make all the equations true. And we call these the intersection points. Or the solution to the system. So circle the solutions to the systems pictured below. So I have this blue line, I have the red line. The solution to that system is this point right here, which will be -2, 1. Let me erase the circle so we can see it. That's the solution to my system. That's the value of x and y. X will be -2, y will be 1. That would make the equations for both the blue and the red line true. Let's look at one that has actual equations. This one right here. X plus y equals 3. That's my pink line. 4x minus 8y equals 12 is my blue line. What are the x and y values that would make both these equations true? Every point on the pink line makes this equation true. Every single point on the blue line makes this equation true. But what is the point that makes both of them true at the same time? That's this point right here, which is 3, 0. So if we plug it in our first equation, 3 plus 0 equals 3, that's true. If we plug it into the second equation, 4 times 3 minus 3 times 0, that equals 12 minus 0, which is 12, which makes the second equation true. And that's the only point that will make both equations true because it's the only point that's on both lines. Now let's find the solutions to these systems by graphing the equations on the same coordinate axes. So I'll pull out my ruler. Let's do the one on the right first. X equals -4. So here's my equation. Oh, now you caught me. Oops, I did it the wrong way. It's x equals -4, not y. 1, 2, 3, 4. Here's x equals -4. And y equals -7. So x equals -4, y equals -7. What's the point that's in both lines? -4, -7. That's the solution to my system. How about y equals 2x minus 3 on the left? So 2x minus 3, my intercept is at -3, and my slope is 2, so up 2 over 1. Let's draw this line. And now let's draw the other line, -5x plus 4. So -5x, oops, sorry. Oh, let me go back. So plus 4, 1, 2, 3, 4. Slope of -5, 1, 2, 3, 4, down 5 over 1. Down 5 over 1. And let's draw my line. So this is the blue one. This is the green one. Where's my solution? My solution, kind of hard to see, but the point that they both intersected in was 1, 1, right here. If we put in or 1 minus 1, sorry, I went down. If we put in 1, 2 times 1 minus 3 is -1. If we put it into the second equation, -5 plus 4 is -1. This is the point that makes both the equations true. And that's visually what the solution to a system of equation is. It's just the point that falls on both lines. The problem with solving it by graphing is sometimes these lines intersect on points that aren't whole numbers. And you really can't tell when you're graphing if they intersect at like a point that's like 1.128 and the y-coordinate is 3.6. You can't tell. So another method of solving is solving by substitution. So here I have an example. Here's a system of equations. It's 2 equations, and I want to solve this for the x and y value that fall on both lines. So your first step is to solve one equation for one variable. So here I chose equation number 2, and I solved it for x. I added xy to both sides, and then I divided by 4. Second step is to substitute this value in for x in the other equation. So for the x in this equation, so I put in my 2y plus 3, I distribute, I combine like terms, I subtract my 9, and I get y equals 1/4. Now I have my y-coordinate, I need to find my x-coordinate, so I simply take either equation. So I can pick either of these equations. I pick the first one, I plug in my y value, and I solve for my x value. Notice it doesn't matter if I pick the second equation, I would get the same thing. If you want to check your answer, plug in both values into either equation, you should get a true statement. My solution is 5/2 -1/4. Those are the coordinates of the x and the y values for the point that falls on both lines. The intersection point of both the lines in our original system. All right, let's try one of these. Or you can turn the video off, try one, and then come back on and check your answers. So notice in my system here, y is already solved for. So I'm just going to take my second equation and I am going to replace y with 6x - 11. So I have -2x minus 18x plus 33 equals -7. I have -20x. On the other side, I have -40. My x is going to be 2. And if my x is 2, my y is 6 times 2 minus 11, or 1. My solution is 2, 1. In the second set of equations, I don't have an equation that's solved for x or y yet. And you can solve for either one, so I look for the easiest. The easiest would be the second one, because I can quickly solve for x by adding 2y to both sides, and now I want to plug that into my first equation. -7 instead of x, it's 2y plus 11. Minus 2y equals -13. Now I distribute. I have -16y. 77 minus 13. 64. So my y is -4. My x, remember, is 2 times y plus 11. 9 minus 8 plus 11 is 3. So I have 3, -4 for the solution to my system of equations. Now there's one more method of solving a system of equations, and that's called finding solutions by elimination. Now, once you do substitution, you're probably thinking, well, why do I need to learn another way? Substitution works great. Substitution does. It works fabulously. If you only have 2 equations and 2 variables, I would go with substitution. It's the easiest way to go. The problem is that in real life, when you have systems of equations that describe complex scientific things or things in the business field, you might have a system of 10 equations and 10 variables. And at that point, substitution gets too confusing, and we use elimination. Elimination is the way computer systems solve, because you can write an algorithm or a program for it that does it quickly and easily. So to solve a system by elimination, you're playing on the fact that if you add 2 equals, you get equals. So what we want to do is we want to manipulate one equation, or maybe both equations. So when we add both sides of both equations, one of the variables cancel out, so we can solve for the other variables. For example, let's look at this first system of equations. Notice 7x and 5x are different. 3y and -y are different. So if I add down, I would get 12x plus 2y equals 6, and that does not help me whatsoever. I have not eliminated a variable. So what we're going to do first, I'm going to write my original equation, my top one. My second equation, I am going to multiply both sides by 3. So I have 15x minus 3y equals 6, and that's a legal move. I can multiply both sides of an equation by the same number. Now, when I add down, look what happens. Positive 3y and negative 3y cancel. and I'm left with 22x equals 14. So my x is 14 over 22, or 7/11. And now solving the system is as easy as plugging in 7 over 11 minus y equals 2. Okay, it's a little bit messy. I have 35/11ths. I'm going to subtract 2 and add y to get y alone. So when I'm subtracting 2, I'm really subtracting 22/11ths. So my y is going to be 13/11ths, and my solution is 7/11, 13/11ths. Notice we would not be able to solve that by graphing. You could not look at a graph and say, oh yeah, that point's 7 over 11, 13 over 11. No, that's too exact for a graph. An elimination solves it nicely. You could solve it by substitution. This is just another way to solve systems. All right, let's look at the second example. Why don't you turn off the video, try the second and third, and then come back, and I will go through them. So I'm noticing in the second equation system, there's several things I could do. I could multiply the top equation by 7. I could multiply the top equation by -2 to get the y's to have different coefficients. I could divide the second equation by -2. I am going to multiply the first equation by 7. So 7x plus 35y equals 63. I'm going to leave the second equation alone. That way when I add straight down, my x's cancel. I have 45y equals, and I am adding straight down, so 63 minus 18 gives me 45. My y is 1. And so my x plus 5 times 1 equals 9. My x is going to equal 4. If you wanted to plug it into the other equation, it would work just fine. -7x plus 10 times 1 equals -18. -7x would equal -28 when I subtract the 10. My x would still be 4. My solution is 4, 1. My last example, what would you do here? So there's no easy way to turn 4 into 10, or 10 into 4, or 2 into 7, or 7 into 2. So what we do is we multiply both equations. So let's say I want to make the y's drop out. I'm going to multiply the top equation by 7 and the bottom equation by 2. So I get minus 28x minus 14y equals 98. And then I'm going to get negative 20x plus 14y equals negative 50. So I get negative 48x equals 48, and my x is negative 1. And then I go ahead and plug the negative 1 into either equation. Pick the one of your choice. I have 4 minus 2y equals 14, minus 2y equals 10, y equals negative 5. My solution is negative 1, negative 5. Now I want to go over 3 special case scenarios. When we think of a solution of equations, let's go down here, we tend to just default to thinking, yeah, 2 lines intersect and we get 1 point. But that's not always the case. Sometimes you have 2 lines that don't intersect, they're parallel. And sometimes you have 2 lines that are on top of each other, so they're intersecting in an infinite amount of points. And what does that look like when we try to solve those equations? Well, let's look at some examples. Let's try to solve the first system of equations here. I'm going to solve by elimination. So I am going to multiply the second equation by a negative number. Then when I add down, I get negative x equals negative 4, x equals 4. If x equals 4, 4 minus y equals 1. My y is going to be 3. This is a case where I have two lines that intersect at one point. All right, case number 2. In this one right here, I'm going to rearrange the second line, or the first line, and I'm going to multiply it by 2. So I'm going to have negative 2y plus 4x equals 2. And I have 2y minus 4x equals 3. I leave that second equation alone. Now when I add down, notice my y's cancel, my x's cancel. I have 0 equals 5. That's a false statement. When all your variables drop out and you have a false statement, you have a case where there are no solutions. And our lines are parallel. There is no point that makes both equations true, so there are no solutions. Finally, let's look in this example. Again, I am going to multiply the first line by 2 and rearrange it. So I have minus 2y plus 4x equals 2. And then my second equation, I'm just going to leave the same. Notice when I add down, the y's cancel, the x's cancel, but I get a true statement. And when I get a true statement, that means no matter which point you put in, no matter what x value and its coordinating y value you put in, you are going to get a true statement for both equations. So that's a case where you have the same line and infinite solutions. So for every x value, you're going to have a y value that makes both equations true, infinitely. So there we go. We've touched base on slope and on lines, how to graph horizontal and vertical lines. Hopefully you did the activity on Desmos to become familiar with slope and y-intercept. We looked at how to calculate slope for a line, how to calculate the slope between 2 points. And then we branched into solving a systems of equations, how to find the point that makes both equations true. We did it by graphing, we did it by substitution, and then finally we found that solution by elimination.